To everyone who is here so far. Thanks for joining us. Mr. Greg Weaver, who is the manager of the observatory, is going to be giving our program. And with that, I'm going to turn it over to Greg.
Okay, thanks, Kim. This is a program that I gave a couple of years ago at the Chautauqua Institute, which is a place up in Western New York where they do all sorts of pretty interesting programs. And I've condensed it slightly to just because there was a lot of extra stuff. This was a program I gave over a 5-day period from Monday to Friday. So I've condensed it a little bit and took a lot of multiple images out. Can everybody see that? The first slide, observing the sky. Okay, so I'm going to assume everybody's good. And if you have any questions.
Yes, we can see it.
Okay, if you have any questions afterward and you think about them, you can email me, send me an email question and I'll get back with you. So without further ado, we'll move on to the next one. So let's see. So what we're going to do, this is about basically how to get started to look up and learn. So we're going to talk about telescopes, how we find things in the sky, and then the way this system's organized, I'm going to start from the surface of the Earth and move out into space and talk about what we can see. So hopefully you all have a telescope, but if you don't, and you own a pair of binoculars, you've got a head start. So the three types of telescopes that are commonly available for amateurs are refractors, reflectors, and things that are called catadioptric, which means they're a combination of refractor and a reflector. They have elements of both. So a refractor is the simplest one. This is the kind of thing Galileo used. And you have a lens in the front called the objective and a lens in the back called the eyepiece. And it's a straight through system. The light comes in the front and goes out the back. Reflectors are a little bit different. They use a mirror to gather the light. And with a reflector, the front of the telescope is here. The mirror is in the back. So the light comes in, bounces off the mirror, and is reflected on a diagonal out the side, because if you had the image would form here otherwise, and if you had your head here, you'd be blocking all the light and you wouldn't be able to see anything. So the light comes in the front, bounces forward, and comes out the side. This is called a Newtonian reflector because it was invented by Isaac Newton. And the last one we're going to talk about is called a catadioptric, which uses lenses and mirrors. So again, it's a straight through telescope. Light comes in the front, bounces off the mirror, bounces forward, then it hits either a flat spot or a secondary mirror here, and it goes out through the back, literally through a hole in the back of the mirror. And these are telescopes commonly made by Celestron or Meade, and they're very compact. This telescope could have a focal length of 100 inches, but the tube is only about 18 inches long. So it's a nice compact system. You can get a large aperture telescope in a small package, but again, they're pretty expensive. Don't forget about binoculars. If you have 7x35 bird watching binoculars, you're already ahead of the game. And if you have 7x50s, they're ideal for astronomy, okay? And if you've ever handheld binoculars before, you know that looking at the stars, everything is jittery and vibrates like crazy, and it really doesn't work very well. But you can attach them to a tripod, and I'm going to show you how that works. So let's see here. I want to get my image on the thing. So let's see. Can anybody see me?
Yes.
Okay, so 735 binoculars. And this is a $10 to $20 binocular bracket. You can buy them at Orion Telescopes, or if you can still find a camera shop, you can probably buy them there. If you look at your binoculars on the front, there's a tapped hole, right? That's a 1/4 20, and these are 1/4 20. And all you have to do is screw this guy in here, like so. Lock it in nice and tight. And then this part here on the bottom is a 1/4 20 thread, and it will attach to the screw thread of your tripod. So now you've got a thing, a pair, two, binocular telescope basically. And when it's attached to the tripod, it won't be shaken. You can aim it up and down, and whatever you're looking at will be rock solid. So if you want to, even if you're looking at the moon through these, you'll see a lot more detail than you will with the naked eye. And if you turn it onto a star cluster like the Pleiades, it'll blow your mind because it has a nice wide field of view and you can see things. The Orion Nebula, the Andromeda Galaxy, all of these things are readily visible in a pair of small binoculars. And it's a great way to start if you don't have a telescope. And again, these brackets are readily available on Amazon. You can buy them at Amazon. You can buy them lots of places. So now I'm going to go back to my presentation. So we talked about binoculars, a great start. So now we're going to move to telescopes. The reason we talked about mounting the binoculars on a tripod is because things are solid and not shaky. Well, any telescope has to have a good mount. Half the cost of a good telescope is the mount. And there are two types, equatorial and altazimuth. So an altazimuth telescope just moves up and down, and an equatorial rotates around the North Pole. And the only reason you would want to have that is for tracking purposes. It's much easier to track with an equatorial mount than an altazimuth. And if you get into photography, you have to be an equatorial mount. Okay. Now, telescope magnification. How much do you magnify? How big does it look? It's real simple. If you take the focal length of the objective divided by the focal length of the eyepiece, that's your magnification. So if your telescope has a 50-inch focal length and you have a 1-inch eyepiece, you're going to have a magnification of 50. A 50-inch focal length with a half-inch eyepiece gives you a magnification of 100. Then the other thing you have to be concerned about is the field of view, or how much of the sky you can see at any one time. And the field of view is simply the field of view of your eyepiece, which is given by the eyepiece, divided by the magnification. So if you have an eyepiece with a 60-degree field of view and your magnification is 60, that's a 1-degree field of view. For purposes of comparison, the moon is a half a degree across. So if you want to look at the full moon, you have to have a field of view of at least a half a degree. So if you had a 60-degree eyepiece and a 60-degree magnification, you have a 1-degree field, so you could comfortably fit the full moon in there. Finding celestial objects, probably the trickiest thing out there. There are certain things that are easy to find, like the moon, like the bright planets. But there are things like a particular double star, if you don't know the constellations. If you're looking for a star cluster, you need to figure out how to find it. Well, we have planispheres. There are websites, computer programs, star atlases. And then if you have a go-to telescope, you're really lucky because once you set the telescope up, all you have to do is enter the object into the keypad and the telescope will go right to it. And then finally, there are celestial handbooks. And all of these things, websites, you can look them up. There are computer programs like Starry Night and Stellarium. And star atlases are just, paper atlases. They look like road maps, except they're road maps of the sky. So here's a planisphere. We sell these at the observatory. And all you have to do to use these is you find the date of the year and you put the time of the night you want to do across from it. So this looks like about, May 15th at 9 o'clock. And this is the sky you would see at that time. And you can tune it in for whatever, any time and any night you want. They're very inexpensive. And the nice thing about them is the batteries never run out on them. So you never end up with a dead planisphere. So if we're starting out on the Earth's surface, the closest thing you're going to see are meteors. And these are fast streaks of light seen in the night sky. And what these are little pieces of debris in space. Typically they're shed from comets and they're only about the size of a grain of sand. But when they hit the Earth's atmosphere at 50 to 100,000 miles an hour, the friction when they hit the air causes it to heat up and burn up, and you see that glowing trail in the sky. Now, there are two good meteor showers in the year, August 12th and the night of the 12th and 13th, that's the Perseids. And we have one coming up December 11th and 12th, that's the Geminids. And the Perseids radiate from the constellation of Perseus, and the Geminids radiate from the constellation of Gemini. And if you have a planisphere, you can find these constellations real fast, and you'll know where to look. The thing about the meteor showers is it's always best to look after midnight, because after midnight, the part of the Earth that's moving through space and leading it, we're on the forward side. So we're running into them instead of having to have them catch up to us from behind. The other trick about meteors is you always want to hope for no moon, because moonlight is like, the moon is one of the greatest light polluters out there. And if you have a full moon, it's going to wash out all the faint meteors. Solar system objects. The first thing we're going to see is the moon, because as you move out from the Earth, that's the first one you're going to run into. It's so easy to see. Any optical aid will do. Even, like I say, even with binoculars, you'll see a lot more detail than you can with the naked eye. So they're best observed in the partial phases. Between first quarter moon is a great time to look, because the line of between daylight and night on the moon is called the terminator. And when you look on the terminator, that low sun angle casts shadows. So mountains and craters and everything, you can see the depth. You can see the shadows, and you can see the light in the dark areas. The toughest part of the moon to look at is the full moon, because it's flat lighting. And if you want to look for the ray systems, that's great. But other than that, you're best to look on a partial phase. And it's always best to use a neutral density filter near the full moon, because the full moon is so bright, it won't hurt your eye, but if you look at the full moon for a second and you look away, you'll see a big purple dot for a while until it fades away. So if you use a neutral density filter, it just cuts down on the total light intensity, and it makes it more comfortable. So as we move out from, here's a picture of the full moon. And as you see, this crater is called Tycho, and you can see these streaks coming out. These are ejected material from the impact. So this is a fairly, young crater, because if it was an old crater, a lot of this stuff would be obliterated by the lava flows here, which are these dark areas. So Tycho and Copernicus have nice ray systems, and Kepler has some rays, and there's one over here called Aristarchus. But like I say, the full moon, the only good thing to look at the full moon is to study the ray systems. So we talked about the phases. Well, new moon is when the moon is between the Earth and the sun and you can't see it. You move to the crescent phase, and when you get the first quarter, then you move past the waxing gibbous, then you reach full moon. Then the moon gets smaller, so you have a waning gibbous, last quarter, a waning crescent, and back to new moon. And the total cycle length is about 28 days to go from this one to the next new moon. The next thing you can look at, moving out, one of the next things is the sun. It's easy to observe, but you have to have the proper filtering, because if you were to look at the sun through an unfiltered telescope, well, first of all, your blink reflex would make you look away. But if you could keep your eye open, the heat and the concentration of light would burn a spot on the back of your retina. And if you could stay there long enough, it would probably boil the fluid in the middle of your eye. So you just don't want to do that. But you can buy filters that'll slip on any telescope. And with them, you can see all sorts of things. You can see sunspots. If you have the proper equipment, you can see solar flares, and you can see prominences on the side. And the sun is always changing. Here's pictures of the sun in white light, and here's two sunspot groups, which come and go with time. And then if you have a hydrogen alpha telescope, you can see these things on the side called prominences, which are places where part of the sun is blowing off due to a magnetic storm, and it grows up and then it falls back to the surface. If you get a really big one, it can actually blow material off the sun and free into space. And if it's pointing toward the Earth when it happens, we can end up with a solar storm, a geomagnetic storm, and we can end up with a big auroral display. Now, auroras are best seen from higher northern latitudes. Maybe once or twice a year, you'll get an aurora visible from our latitude, but there's been a couple of alerts in the last couple of weeks about a possible aurora, but nothing panned out for us, unfortunately. We're too far south. Let's talk about the planets. There are 5 visible planets that you can see with the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. Mars, Jupiter, and Saturn are the most interesting ones to look at with the telescope because there's things to see. Every 2 years, Mars gets very close and it gets fairly big, and you can see some surface detail. Jupiter is always a good thing to look at when it's far enough away from the sun, because Jupiter has cloud belts, which are interesting, and it has 4 moons, which are constantly shuttling back and forth in front of and behind the planet. And oftentimes, when the moon goes in front of Jupiter, it'll cast a shadow on Jupiter, and you can watch the moon and the shadow move across the disk. And Saturn, of course, is always spectacular because of its ring system. Mercury and Venus are tough to see. Venus isn't tough to see because of its visibility, but Venus is covered in thick clouds. So all you see is if you look at you can see Venus right now in the west at sunset. It's that very, very bright white star. And you'd think, wow, that must be something to look at in a telescope. But if you do, you're going to be very disappointed because it's just a bright white object with no definition, because you're just looking at cloud tops. And Mercury is tough to see because it never gets very far from the sun in the sky. And if you do get a telescope on it, Mercury is very small. It's not a whole lot bigger than our moon. And it's so far away, it is tiny. You'll see a crescent shape or maybe a quarter moon shape, but you won't see any detail on the surface. And it's never far from the sun, so it's always low in the sky. Not much to look at. It's more impressive visually than it is with a telescope. Okay, now these 3, what I call the big 3: Mars, Jupiter, and Saturn. So there's Jupiter in a big scope. And here you can see this is one of the moons, the shadows of one of the moons going across Jupiter. And here you'll see something, this is called the Great Red Spot, which in a moderate sized telescope, if the Great Red Spot is facing us, it's easy to see. But you could very easily look at the Jupiter and not see it, because Jupiter rotates in 10 hours. Well, every 5 hours, you see a different side. Right now, if Jupiter's going this way, in about 2 hours, the red spot will rotate around the back side and it'll be invisible. So you have a 50-50 chance of seeing the red spot if you look at the Jupiter with a telescope, because it's on the back side, you won't see it. This is a picture I took through my telescope, and this shows the moons. And as you can see, here's all 4 of them. On one particular night, it would look like this. On the next night, these could be in completely different places. Now, this is Jupiter, and it would look like this, except I had to overexpose it to pick up the moons. But if you look at it in a telescope, it would look like this, and you see these 4 stars always in a line. And in a couple hours in a night, you could see a difference, because the inner one, Io, goes around the planet in just a couple of days, so it moves very quickly. And you can actually watch, if they were lined up correctly, you could watch the shadow going across the surface of Jupiter. Here's Saturn. Right now, Saturn its rings are fairly well open, and it's in the west. It's almost in the due south at sunset. If you look to the south at sunset, you'll see a really bright star. You see Venus in the west, southwest. Due south, you'll see a bright star. That's Jupiter. And to the left of that, you'll see a little fainter star. That's Saturn. So right now, Venus, Jupiter, and Saturn are easily seen in the evening sky. Now, Saturn's rings go through a tilt period. Sometimes they're edge on, and during that period of time, they're actually invisible. But as you can see from these dates, the rings open up and close with time. So right now, the rings are fairly open, and it's a beautiful thing to look at and easy to find. Next out from the sun, we have the region of comets. And comets can either come from the Kuiper belt or the Oort cloud. Right now, there aren't any bright comets that are scheduled to make a visit. But if you remember last summer, there was a comet called Neowise, and it was visible to the naked eye in the dark sky. I was up at Cherry Springs State Park last summer, and you could plainly see comet Neowise with the naked eye. So these things, they come and go. There's no predicting them really. Typically, you might have 3 to 6 months notice when a bright comet is discovered. When it's discovered, it'll be far away from the sun and not probably invisible to the naked eye. But as it approaches the sun warms it up, and these comets are made of ice and dust. So as it warms up, the ice evaporates, sublimes, and it releases the dust, and that's what forms the tail. So comets, naked eye to binoculars are pretty good to see comets. This was Neowise last summer, and this was a time exposure, but you can see it was quite bright and it had a fairly long tail. And it was in the region of the sky. It was near the north celestial pole, so it was actually visible all night. It was actually rotating around as the night progressed. It was a beautiful comet, one of the brightest we've had recently. Okay, then we get to the Milky Way, which is our home galaxy. And everything we've talked about so far is in the Milky Way. And almost all of the stars you'll see in the sky are part of the Milky Way. Unfortunately, with our light pollution, it's very difficult to see the Milky Way from this area. But if you can get out to a dark sky location, you can actually see the Milky Way, the band of Milky Way stretching overhead. I was in Yosemite about 2 months ago, and the Milky Way, the summer Milky Way, was directly overhead, and it was just beautiful. It looked like a cloud, except of course it wasn't moving because it was not a cloud, it was a cloud of stars. And there are 88 constellations in the Milky Way. And if you have a planisphere or a star atlas, you can look at them. And there's even, if you have a cell phone with any kind of a, smartphone, there are programs both for iOS and for Android phones. And all you have to do once they're installed in the phone, you hold your phone up and you point it to a spot in the sky, and it will identify what you're looking at. It'll show you the constellations and the stars, and you identify the planets for you. Anything that's up there, it'll tell you what. All you have to do is hold it up to the sky, and wherever you're pointing it, it'll explain what you're looking at, which is a very, very, very nice way to learn the stars nowadays. With the telescope, things get interesting. You can see multiple star systems called double stars or even triple stars. And they come in all sizes, brightness, and colors. Sometimes the middle star in the handle of the Big Dipper is called Mizar, and it's two bright white stars about the same brightness. There's a star in Cygnus called Alberio, which is at the tip of the swan, the nose of the swan, and one of the stars is gold and one of them is blue. So with double stars, you almost have to look at them and you never know what to expect. You can get same brightnesses, different brightnesses, same colors or different colors. So this is Alberio, and you can see the brighter one is kind of yellowish and its companion is blue. Over here, this is Castor, which is the alpha star in Gemini. And these two right here are almost the same brightness and they're both white. And then we have what's called the double-double in Epsilon Lyrae, where you have two what look like single stars, but when you magnify them, each one of them is also a close double. So it's a quadruple star system. So as I say, you never know what you're going to get with double stars. And even a small telescope will show you a lot of different stars. Then we have star clusters in the Milky Way. We have open clusters and globular clusters. Open clusters are groups of stars that form from the same gas cloud, and they can be anywhere 6 to thousands of stars, and they're within the Milky Way. Globular clusters are spherical balls of stars, large numbers, 50,000 to 500,000 stars, and these clusters orbit the Milky Way the same way the planets orbit the sun. So these are two open clusters. This is called M11. This is a summer open cluster in a constellation called Scud on the Shield. And this is M36, which is it's an open cluster in the constellation of Auriga. This is something you can see in the wintertime. Then these are globular clusters. This is M4, which is in the constellation of Scorpius. And this is a very rich cluster called M5, which is in the constellation of Serpens. And this is just a gorgeous thing and 6-inch to 10-inch telescope. In binoculars, you wouldn't be able to resolve this because you need a lot of magnification to see these, but in a telescope with a magnification of 100 or more, these things start to show their true splendor. Then we have, now well, nebula are glowing gas clouds, which are in the Milky Way, and they can be either dark nebula or glowing nebula, depending on whether there's a bright star in the vicinity causing the gas to glow. This is called the Trifid Nebula, which is in Sagittarius. And there are bright stars in here which cause this gas cloud to glow. They excite the gas cloud to glow in specific frequencies. And in this gas cloud, this is an area where stars are forming right now, where there's collapse going on and new stars are forming. So when you see a nebula, you know it's a very young region of space with very young stars in it. This is the Orion Nebula, one of the prettiest ones you can see, and one that looks pretty good in binoculars. So this is a black and white image, and this is a color image. This entire area is a giant cloud of gas. But this area here has 4 very large, very hot stars called the trapezium, which cause the entire gas cloud to glow. Much the same way a fluorescent light bulb glows because you have gas in the tube that's being excited by electrons from the filaments. Well, you've got 4 giant stars that are acting like filaments to excite this gas in this area of space. Here's dark nebula. We have a gas cloud in the background, but between us and the gas cloud, there's another gas cloud which doesn't have any stars in it to excite it. So it's dark, and the gas and dust blocks the light from behind us. So what you're seeing is a silhouette of a near nebula and a far nebula. It's called the horse head because it looks like the head of a horse. Finally, the last thing we're going to talk about is external galaxies, which are very faint, and you just don't see much detail unless you have a large telescope. And I'm talking about 12-inch telescopes and larger. And you also need a dark sky for maximum contrast, and we don't have dark skies around here. You need to travel to a dark sky location, which means getting at least 50 to 60 miles away from a large city. So here's the Milky Way, right? There's the center. And our sun is right here, located in one of the outer spiral arms. And so when we look out, when we look in this way to the summertime, we see the center of that galaxy. And when we look out here, we see things like Orion and Perseus and various star clusters. And these clouds here, you notice these red and blue clouds? Well, these are the emission nebulae I was talking about. And finally, we have the Andromeda Galaxy, which is the closest large galaxy to us, visible to the naked eye on a dark sky location, and it's in Andromeda. And you have a large spiral galaxy, which is very much like the Milky Way. And there are 2 companion galaxies. Right here is, the big one is called M31. Then this is M32, which is a small spherical galaxy. And out here we have M110, which is also a satellite. This was originally a small spiral, but the gravity of this one has disrupted it and torn it apart. And it's actually pulling it in. In millions of years, this guy will be sucked into the big one, and so will this one, and they'll be dispersed and no longer visible. Then these are 2 others I like to show. This is called the Whirlpool Galaxy, and it's just off the handle of the Big Dipper, and it has a companion galaxy right here. So this is a galaxy, a spiral galaxy seen face on. Then this is another spiral galaxy, which is seen edge on. So you can see the spiral galaxy is very thin. And so these are the same arms that you see here, but instead of looking at it from below, up above or below, you're looking at it edge on. So these are called needle galaxies. And this is a galaxy in Coma Berenices, which is not very far from this one actually in the sky. And then finally, we have elliptical galaxies called this one's M87. And it's just a giant, think of it as a super big globular cluster. It's a giant sphere of stars. and it doesn't have any structure like a spiral does. And it doesn't have a whole lot of gas and dust to form new stars like spirals do either. So this is kind of reddish because it doesn't have any gas in there to glow blue and reflect blue and generate new stars. So these are older galaxies.